Jai Hind everyone. So today I am going to discuss the topic related to the subject cryptography and network security. It is a 7th semester subject. So I am Shilpi Gupta from Department of Information Technology, Ajay Kumar Garg Engineering College. So the topic which we are going to discuss today is Feistel Cipher structure. Before discussing this subject, this topic in detail, we need to know the basic necessary requisition or requisite for this topic, that is block and stream cipher. The block cipher is something which is taken in a form of a block. Means the main thing is to keep our data secure, the information whatever we are sending on the open network, to keep it secure. So how we are going to keep that information secure in a coded way? For that purpose, we are going to process our input in two forms. First one is block cipher, second is stream cipher. So in block cipher, we process the messages in the form of block, each of which is then encrypted or decrypted. Encryption will take place on the sender side and decryption will take place on the receiver side. Like a substitution on a very big character, basically we are going to deal with 64 bits or more, not less than that. The stream cipher process messages a bit or byte at a time when encryption or decryption takes place. So it is very much clear that if we are talking about the block cipher or a stream cipher, in block we are going to take a collection or group of bits, and in stream cipher we will process it one by one bitwise. Many current ciphers are the block cipher. There are a broader range of applications available for the block cipher. So coming to our actual topic, that is Feistel Cipher structure. This Feistel Cipher structure, you can say, is a base of all other important mechanisms or techniques which we are using frequently to keep our data secure on the network. So the Feistel Cipher structure, it is basically developed or generated by host Feistel, which named as the Feistel Cipher. Based on this concept, it is basically the invertible product cipher. In this, basically the partition of input block into two halves takes place. Then we process it in the form of multiple rounds, which perform the substitution on left data half. Based on round functions of right half and subkeys, the permutation swapping of halves takes place. It is also implemented for the Shannon's SP net concept. So in general, if we are talking about the Feistel cipher structure, it is a base of many other techniques or mechanisms which we are going to use to keep our data secure on the open network. We are going to divide our information into two halves, the left half and the right half. Those left and right half are going to be processed one by one, and finally the information will remain secure so that no other third party or third person will get easy access to it. So this is the actual structure, how the Feistel cipher is going to be implemented. You can see over here in the beginning, we are having the information which we want to send on the open network. So we call it as the plain text. Initially, I am writing here it as a 2W bits because, as I have already told you, we are going to divide it into two halves and then we will process it. To divide it into two halves, I am calling it as 2W. The plain text bits 2W will be divided into two parts over here, two equal halves, the left half and the right half. The left half bits will be the W bits, the right half bits will be the W bits. In the first left half, you can see I am going to denote it with the help of a naught, L naught. Right bits will be the R naught. For this first round, you can say left naught bits will go for processing. The right naught bits will be processed with a function, or you can say the capital F, denoted as the Feistel cipher function. Both of them will be XORed over here. After performing the XOR of left half and the right half bits, those right half bits are not only the actual right half, but those right half which is already processed with the Feistel Cipher function. Those processed bits will be XORed with the left half bits. When this XOR will take place, finally whatever is the output from this XOR, it will go as an input to the right half. It will become R1. From here, whatever R0 bits, R0 bits are there, they will go to the left half and will become the L1. So you can see over here, whatever bits are coming, we are processing it, and those bits after processing will be carry forwarded forward into the next round. So you can see a number of rounds are going to be performed, and only after performing all those rounds, the information or the ciphertext which is generated at the last is much more secure than the previous information. So these bits are divided into two halves, left half and right half. The left half round will go for the XOR along with the right half bits. These right half bits are not the actual bits, they are processed into this Feistel Cipher function. After performing this XOR, it will go to the next round, and these left half will become the right half, and these right half will become the left half. These rounds will keep on repeating again and again. You can see over here, this is the round 1, round 2, round 3, and so on, depending upon how much time you want to process these bits, and the number of rounds will decide how much secure this information will be on the receiver side. So here again, just repeating the first round again, the bits which are coming from the previous one, means the output of the previous one will act as the input to this next round. These R bits will again go to the Feistel Cipher function. Here, these bits are directly coming to the round process for this XOR function. After the XOR operation on these two bits, the left one and the processed right one, the output will again act as the input to the next round. So the output of first round will act as the input to the next round, and in the same way we are keep on repeating the number of rounds. So here we are not defining the number of rounds, we can increase or decrease the number accordingly whenever we want. So finally at the last end, at the last of this particular round, you can see there is certain changes. This Ln means left side of this number of n rounds and the right side of this nth round will act and go to the left and right side, and finally combine these two halves, and it will produce the final output on the receiver side. As you can see, initially we started with our 2W bits. The input is of size 2W. I have assigned this value as 2W because we have divided into two equal halves. So 2W is divided as W and W on the left and right side. In the same way, finally these two halves are going to be combined together, and they will create or contribute to the ciphertext. So this is a general structure, you can say, which acts as a base to many other mechanisms and techniques. These are the main elements which contribute to the Feistel Cipher design. The block size. Block size means whatever block or part of that input we are going to process, what is the size of that block? That plays an important role. Second is key size. Which particular size of key we are taking to process this block? That also creates, or you can say that also provides an important factor for this Feistel Cipher security. The number of rounds, we can increase or decrease the number of rounds according to the requirement, which kind of information we are sending, how much security the information requires. Accordingly, we can increase or decrease the number of n. Sub-key generation of algorithm, whatever algorithm or Feistel Cipher function we are using in between. You can see over here, whatever logic we have used over here at this point F, that also plays an important role. The round function, fast software encryption and decryption, and we need something which is very easy for analysis. So all these are the important elements which contribute for designing of this Feistel Cipher. So as we have already discussed the basic structure of Feistel cipher, now I am going to talk about the actual encryption and decryption part for it. You can see over here, the input is there. Again, we are going to divide this input into two halves, left and right half. Here we are not showing the actual number of bits because number of bits can vary. If our input is of 64 bits, then we are going to divide it in 32 and 32. If it is of more, then accordingly it will divide it into two equal halves. But the condition is we always keep the minimum number of bits as 64 bits. We cannot use less than that. We can increase, we can use more than 64, but the minimum requirement is of 64 bits. So this left half and right half is going to be processed. Here in this Feistel function, the capital F, we are going to apply the actual key. You can see here in the previous slide as well, the block size and the key size both plays an important role. So here, this function is going to be processed with a key. Generally, we use a 52-bit key. This 52-bit key is processed with this Feistel cipher function. Whatever logic is used over here, the combination, permutation and combinations will take place, and after finally those combinations, whatever function is generated, it is going to be processed over here for XOR function. So this left half will be there. You can see the right half is coming. This right half is going inside this Feistel cipher structure, the function. Key is processed over here, and finally it will produce the output for performing the XOR function. You can see over here, XOR is performed and output will come. This output is straightforwardly going for the next round. I am again going back just to compare this actual structure with the encryption or decryption structure. You can see this actual structure. Here what we are showing, after processing whatever we have produced, it is going to be exchanged. Means left half will act as a right half and right half will act as a left half. And here what we are doing, we are just showing it a straight. If we are going this as a straight line, we are not interchanging it, then we need to change our direction. You can see over here, the key is coming to the function and we are performing the XOR on our left hand side. Here we are performing the XOR on the right hand side. So like this, both the things are same. Just you need to remember how you are going to draw your diagram. So this left half and right half are going to be interchanged. Here we are going to process it for 15 rounds. As you can see, we have started with LE0. That is left encryption 0, left encryption of very first round. Here is the right encryption for the very first round. And it will keep on going like this in the same way, in the same pattern. Finally, coming to the last one, you can see over here it is written 16. We have started with 0. Here it is written as 16. One by one, whatever the output is, again we need to combine it to make a complete ciphertext equivalent to our input. Our input started with 2W, so our ciphertext will end up with 2W. So we need to keep these two things equal. Coming to the decryption part over here, we will start from here. Now this ciphertext will act as the input. You can see that this ciphertext will act as the input now. Whatever is the output over here on the sender side, sender has an input plain text, processed it through the various rounds for the Feistel cipher. Here we are having the output, that is ciphertext, which is a processed data. Now this processed data reaches to the receiver side on the another side. When this receiver receives it, means it will act as an input now. This ciphertext is the input for this receiver side. Now we will start processing from here. It is just a reverse for this encryption part. Whatever we did over here, it is just a reverse of it. You can see the input is there, key will be there. We are going to divide it into two halves. Here we are going to denote it with LD and RD. That is the left and right decryption part. Here it is for the encryption part, E. Here is for the decryption part, that is D. XOR will take place, certain functions, Feistel functions are there. We are going to process these Feistel functions within key, and one by one again we are going to perform the same steps but in the reverse order. Here we started with input plain text, output is the ciphertext. This part we are having the ciphertext as an input, and finally it will produce the plain text. So again you can say we are having the output of the plain text over here. So this is all about our Feistel cipher structure. This Feistel cipher structure plays an important role, or you can say it's a base of many other techniques. So after this we are going to talk about the DES, that is data encryption standard. In this data encryption standard, you can see this particular kind of encryption technology is widely used with the help of block cipher in the world. It is adopted in 1977 by NBS. Now it is NIST. It encrypts the 64 bits data using the 56 bits key, and it is widely used all over the world. Talking about the history of this DES, it is developed by IBM. Initially it is known as Lucifer Cipher. By time the team led by Feistel, as you know, the inventor is the Feistel. It uses the 64-bit block with 128-bit key. Afterwards, that number of keys also processed, and we reduce the number of keys from 128 to 56-bit. Then redeveloped as a commercial cipher with input from NSA and others. In 1973, the NBS issued the request for proposal for the National Cipher Standard, and it submitted the revised form of it, and finally, eventually it is accepted as a DES, that is data encryption standard. So how this DES actually works? This complete complex diagram shows the actual working and processing of it. Here we have a plain text of 64-bit. We are taking a key of 64-bit. This plain text will go through the IP. We call it as IP ensure, that is initial permutation. What this initial permutation basically means we are going to rearrange our input in certain order, and we will change its order, that is the initial permutation. We will discuss the individual things, whatever written over here, in detail afterwards, but right now it's a complete general diagram to show the DES encryption overview. As an input, we are taking the 64-bit plain text. It will come over here, we will perform the initial permutation on it. After performing this initial permutation, we are having a 64-bit information with us. The 64-bit information will go to round 1. We are calling it as round 1. Here on the right side, you can see we are processing the key. We have 64-bit key altogether. It will go through the permutated choice 1. Permutated choice basically means the input of 64 is reduced to a number of 56 by certain combinations and orders. That choice has been done, and we have discarded some of the bits, and finally out of 64 we are using 56 bits. So the 56 bit will go through the left circular shift. We will perform the left circular shift on it. Whatever number of bits we are having in total, we are going to perform the left circular shift on it. Now here we are again performing the permuted choice 2. Here you can see it is permuted choice 1. Now we are performing it for the second time. This is permuted choice 2. After performing permutations and all, we have reduced the number of bits from 56 to 48 now. So initially it is of 64 bits. For the very first point, we have taken the key of size 64. We have reduced it to 56, and again for the second choice we are reducing it to the 48. This is round 1. whatever input is coming from this initial permutation of 64 bits and whatever key is coming out of this 48 bits, both of them are processed over here and they will produce a final again output which will act as an input to the next round. So here you can see that how the processing done in a particular round contributes as an input to the next round. So here's the round 2. Here, whatever we are having out of this left circular shift, again those bits will act as an input to the next round, and these key bits are again processed for the left circular shift. They will come over here for their again the another permitted choice. Out of that we have selected 48 bits, and those 48 bit key will act with these 64 bit plain text. So what you can see that one by one, whatever plain text is going to be processed on the left hand side of our screen, you can see all those things are going to be processed with these keys. In each and every round we are processing it with the certain number of bits in the key. Here in round 2 again, the 64 bit plain text is processed with the 48 bit key. Side by side we will keep on going to do it like this, and in total we are going to use 16 rounds in our DES encryption method. All these rounds are similar to each other, only the difference is we are changing the value of bits in each and every round by passing those bits through their certain permutations, combinations and all. Actually what this permutation does, what this initial permutation does and what these rounds are doing, we will discuss it in detail in our next slides. But for now you can see the overview that how the output from a particular round plays a very important role for the next one. Any correction or any problem at a particular point will obviously result to the changes of bits in our further rounds. So we need to be very much careful while processing all these bits. Now after this round 16 you can see this left circular shift is finally being done. It will go to the permitted choice 2. Finally we are having a 48 bit which will be processed over here in the round 16 and output will come. Whatever output we are having after this round 16, it will be swapped with 32 bits. The initial permutation has been done. Now we are going to perform the inverse of it, and output will be the 64-bit ciphertext. It is a very secure ciphertext. It is not easy to crack. So now all these important things which you can see in this particular slide, we are going to discuss it in detail. The very first thing is initial permutation. The very first round of this DES method is initial permutation IP. What we are doing here, we are just dividing our input data into two halves, left half bits and right half bits. Even bits to the left half, odd bits to the right half, and now we are going to use this left half and right half individually. As you can see, initial permutation is written over here. Input is of 64 bits plain text. Here in IP, what we are doing, we are just dividing our information or plain text into two halves depending upon the odd and even. So even bits to the left half and odd bits to the right half. This is the initial permutation. DES round structure. So the actual round, what logic is used behind those 16 rounds, it is explained over here. Using two 32-bit left and right halves. Why we are calling it 32-bit left and right halves? Because as you know, our input is of 64 bits in total. If we have divided into two equal halves, it means each half has 32 bits in them. So uses two 32 bits left and right halves for this. What this left and right half is going to perform, you can see over here, if we are taking Li, what this Li means if we are talking about left hand side. I means if we are taking it for round 1, means Li means L1. It is equal to Ri minus 1. I'm taking the value of I as 1, means this is the round 1. L1 is equivalent to Ri minus 1. What is this? It means L1 is equals to R0. Yes, because we are changing the value of left and right. So whatever is the output from the previous one, it will act as the input to the next one. Here you can see we are talking about Ri. If I am talking about R1, then what we are going to do? L1 minus 1 is XORed with the function of R1 minus 1 and key 1. This is somewhat like this. Yes, going back to that particular slide, it is a process of key and these write bits, they are processed together. I'm again going back to the Feistel Cipher structure. You can see over here, this Feistel Cipher is actually playing a base for this DES. So because of that, you can see over here the right half, it is processed with the function, this Feistel function, and this key, which is going to be XORed with the left half, and finally it is produced as an output, and it will go to the right hand side. And this right half is directly going to the left hand side. So from there you can easily understand what will be the value of these left and right halves. Those left and right halves are discussed over here. This left half is equivalent to the previous right half bits. This right half is equivalent to the previous left half XORed with the function, this Feistel cipher of right processed with the key. So in the same way, you can see if we are talking about the round 1, the very first round, where the value of I is equals to 1, you can see we are having this. Means left half values will come from the right half straight. Previous right half to the next left half. In the same way, if we are talking about R1, this right half is equivalent to the previous left half. You can see 1 minus 1, it will give you L naught. XORed with the function of this R0 and K1. Alright, so you can see that how these two things will finally contribute to the next right half. F takes 32 bits of right half and 48 bits of subkey, expands R to the 48 bits, then add subkeys to it. We will perform the XOR to it and passes through 8 X boxes to get 32-bit result. Finally, permutes using 32-bit. So this is the round structure. These 32 bits of right half will be processed with the help of an encryption. 48 bits key will be processed over here and XORed with the 48 bits key. Means whatever input of the right half is having, we are going to expand that. These 32 bits will be expanded to the 48 bits and these 48 bits of key will be processed over here. The XOR will take place and they will be processed through these substitution boxes. What these substitution boxes are doing? They are channelizing these 6 bits to the 4. 6 bits to the 4 like this, and total we are having 8 X boxes. And finally, we are having 32 bits. So these substitution boxes, we can denote it by S. What they will do, they have 8 X boxes which map the 6 bit to the 4 bits. You can see 6 bits are coming as an input to a particular S box, substitution box, and finally it is producing a 4 bit. Out of 6, it is producing 4. So in the same way, we are having 8 X boxes which map the 6 bit to the 4 bits. Each X box is actually the 4 little 4-bit boxes. Outer bit 1 and 6, that is row bits, select one row of 4. Inner bits of 2 and 5, that is column bits, are substituted. and result is 8 lots of 4 bits or 32 bits. So finally, what is 48 bits we are having as an input? Finally, we are producing the 32 bits out of it, because it is taking 6 bits as an input and producing 4 bits. 6 bit as an input and 4 bits as an output. So row selection depends on both the data and key, feature known as auto-claving or auto-keying. So after discussing all this about the DES structure, data encryption standard, which is dependent on Feistel Cipher, we are having the Avalanche Effect, key is desirable property of encryption. So where a change of 1 bit or 1 input key bit will result to the changes approximately half output bits. What basically it means? This Avalanche Effect says that if there is a change in a single bit, means 1 is converted to 0 or 0 is converted to 1, means any of the bit change, a single bit change, will affect to approximately half of the output bits changes. So this is a very important thing related to data encryption standard, that is the Avalanche Effect. Strength of DES is it's our key size. You know very well we are using a key of 64 bits in DES. If anyone is going to perform this brute force attack or brute force they want to try, means they will keep on trying these certain combinations, different combinations of key to crack the information. So if we are having 64 bits key, so you can analyze, it means this much number, 2 raised to the power 56 number of combinations are there. Approximately this value will come. So it's a quite large value to try to crack some information, to crack anything. So this is the very important thing or important factor, you can say, how this DES is so strong. So the strength of DES is its key size. Key size is of 56 bits. If we will find out the possible number of combinations, it will produce this much value, and which is actually very large, a huge value to be performed with the brute force search. So this is all about our today's lecture. So this is the summary what we have all discussed. We have talked about the block and stream cipher in detail. This block and stream cipher, we have talked about the Feistel cipher structure and design. This Feistel cipher structure plays a base for this DES structure. We have discussed the DES in detail and talked about its strength as well. So this is all for now. Thank you.